Hi. I'm Paul. And I'll be guiding you through this training. Here are the objectives for this course. In this module, you'll learn about the atom. So what is an atom? As we learned from the last module, all matter is made up of elements. Remember, elements are substances that cannot be broken down any further by chemical activity. Remember also, where we can find a table of all the elements. An atom is defined as the smallest particle of an element that can exist either alone or in a combination with other atoms of that element. Atoms are considered the building blocks for everything in the universe, including ourselves. People often think of atoms as the smallest possible forms of matter. But even smaller particles make up atoms. As a group, these particles are called subatomic particles. The three main subatomic particles that form atoms are protons, neutrons and electrons. Let's take a closer look at those three particles now. Each atom has a dense center called the nucleus. The nucleus contains neutrons, which have a neutral electric charge, and protons which are positively charged. The number of protons in an atom determines an element's identity. No two elements have the same number of protons. Revolving around the nucleus in the area of the atom called the electron cloud are negatively charged particles called electrons. Electrons and protons attract one another. Neutrally charged atoms have equal numbers of protons and electrons. Scientists assign atoms an atomic number and an atomic mass number, which is measured in atomic mass units or AMU. The atomic number is the number of protons present in the atom. For example, a helium atom has 2 protons. So helium's atomic number is 2. If you add the number of protons and neutrons in an atom together, you get the atomic mass number, measured in AMU. A helium atom has 2 protons and 2 neutrons, so its atomic mass number is 4 AMU. Electrons have virtually no mass, so they are not included in atomic mass number calculations. Not all atoms of an element are exactly the same. While the number of protons in an atom of a particular element remains constant, the same element can have a different number of neutrons. These are called isotopes of the same element. Isotopes are atoms with the same number of protons but having a different number of neutrons. Or, an atom with the same atomic number, same element, but with a different atomic mass number. For example, this is carbon-12. It is the most common form of the element carbon. It has 6 protons and 6 neutrons, thus the atomic mass number is 12, hence the name, carbon-12. This is carbon-13. This carbon atom has an extra neutron, giving it an atomic mass number of 13. Therefore, this is an isotope of carbon. This is carbon-14, another isotope of carbon. This carbon atom has 2 extra neutrons, a total of 8, giving it an atomic mass number of 14. All elements have a number of isotopes. Hydrogen has the fewest number of isotopes with only 3. Cesium has 40 known isotopes, making it, along with barium and mercury, one of the elements with the most isotopes. Now let's talk about ions. Atoms with the same number of protons but different number of electrons. A normal atom has the same number of protons and electrons and has a net charge of 0. When ions are formed, the atom has a net positive or negative charge. A positive ion is formed when an atom loses 1 or more electrons. A negative ion is formed when an atom gains 1 or more electrons. The process by which ions are created is called ionization. Once again, let's look at helium. Normal helium has 2 protons, positive charges, and 2 electrons, negative charges. So, because normal helium has the same number of positive and negative charges, the charges offset each other, and normal helium is neutrally charged, or has no charge or is, not, an ion. If helium loses 1 electron, it becomes a positively charged helium ion, since it has a net positive charge because it lost 1 negative charge, the electron. This ion is designated as the chemical symbol for helium, He+. If helium loses 2 electrons, it becomes helium++ or helium-2+, which as you can see is just a helium nucleus without any electrons. You'll learn later in nuclear science that another name for this helium nucleus is an alpha particle. Here's an example of how a negative ion is formed. If neutral oxygen, with 8 protons and 8 electrons, gains 2 electrons, it becomes an oxygen ion. Since it now has a net +2 charge, it is a negative ion, designated as O- or O2-, commonly known as the oxide ion. Positive and negative ions and determining which is which may be a little confusing, so here's a little trick that hopefully will help you remember. Notice the word lose, spelled L-O-S-E, has an O and an S together. Just like the word positive. So, to become a positive ion, the atom must lose 1 or more electrons. Also, notice the word gain, spelled G-A-I-N, includes the letter N, just like the word negative. Therefore, to become a negative ion, the atom must gain 1 or more electrons. Recall that electrons are located in the electron cloud surrounding the nucleus. But electrons do not simply fly around the nucleus randomly. Instead, they occupy specific levels called electron shells, and each shell can only hold a set number of electrons. The first electron shell can hold up to 2 electrons. The second, and in most cases, subsequent shells, can hold up to 8 electrons. The electrons in the outermost shell are called valence electrons. Now, ideally, atoms would like to have their outermost shells filled to capacity. Meaning, in most cases, 8 electrons. Atoms with completely filled outermost shells are stable, meaning they don't react easily. Their outermost shells are full. These atoms are content, or stable. Atoms with an excess, or deficiency of electrons in their outermost shell tend to react or bond with other atoms when given the opportunity. Helium and neon are examples of stable atoms. Hydrogen, lithium and sodium have only one electron in their outermost shell or one valence electron. These elements are not stable. This is aluminum. It has 3 valence electrons. This is chlorine. How many valence electrons does it have? The periodic table of the elements contains pertinent information about all the elements. The periodic table is arranged in order of increasing atomic number, that is the number of protons in the atom of the element. A copy of the periodic table, similar to the one shown here, is included with your chemistry exam reference material. Or, you can Google periodic table and find a wide assortment of printable tables. Keep in mind though, on the exam, you will only be allowed to use the periodic table provided in the reference guide. Let's take a look at the element zinc. Remember, the elements are arranged in numerical order, by atomic number. Zinc has atomic number 30, which means an atom of zinc has 30 protons. The atomic number defines the element, as no other element has an atomic number of 30. The elemental symbol, or abbreviation for zinc, is Zn. You'll find that some of these symbols are pretty straightforward, like Zn for zinc and H for hydrogen, and some are not as straightforward. That number at the bottom of the box is the atomic weight. More about that later. Now let's talk about how the periodic table is organized. Elements are put in rows by increasing atomic number. The horizontal rows are called periods. The vertical columns are called groups. Each group, also called a family, is identified by the number at the top of each column. All elements within a group have similar characteristics or properties. This is because elements within a group have the same number of valence electrons. You may have noticed the 2 rows at the bottom that are separated from the other elements. This is just to make the periodic table we use more compact, and not so wide. Here is where the 2 rows would be inserted. All elements are classified on the periodic table as either a metal, indicated by the gray, non-metal, indicated by the gold, or semi-metal, indicated by the blue. One of the first things you may notice is that there are way more metals than non-metals, and there are only a few semi-metals. First, let's talk about metals. Metals are considered good conductors of heat and electricity. That means that heat and electricity will easily flow through a metal. Most metals are solid at room temperature, the exception is mercury, which is a liquid at room temperature. Metals are malleable, meaning they can be beaten or pressed into sheets. Metals are also ductile, meaning they can be pulled into wire. Metals are shiny in appearance, and are usually gray or silver in color, with the exception of gold. Non-metals are good insulators of electricity and heat, meaning they are poor conductors. Most non-metals are liquids or gases at room temperature. Those non-metals that are solid are brittle, in other words, not malleable or ductile. Non-metals are generally dull in appearance, and their colors vary. Reactivity is defined as the tendency of a substance to undergo a chemical reaction either by itself or with other materials. Reactivity tends to increase as one progresses outward on the periodic table. Elements on the extreme outsides of the table are the most reactive, with the exception of the noble gases, which are not reactive at all. The elements that are the most reactive are those that are closest to having the ideal electron configuration. Do you remember what the ideal electron configuration is? That's right. 8 electrons in the outermost shell. Elements on the outside of the table need to gain or lose fewer electrons to achieve a filled outer shell than those elements in the middle of the table. So, let's look at two elements, sodium and aluminum. Based on their locations on the table, and what we just learned, which element would you say is more reactive? The answer is sodium. Why? Because its location is closer to the outside of the table than aluminum. Reactivity is affected as you go up and down the table as well. For groups 1 and 2 elements, reactivity increases going down the column. This is because atoms of each element get larger going down the group. These elements are electron donors, that is, they have relatively few electrons in the outermost shell and would be more prone to give up their electrons to become stable, that is, having 8 electrons in the outermost shell. These valence electrons are further away from the positive nucleus, so they're not held as tightly as smaller atoms with electrons closer to the nucleus. In other words, the further away the electron is from the nucleus, the easier it is to get picked off by an electron receiver. This makes it easier for an electron receiver to react with that element by taking electrons away. For group 6 and 7 elements, reactivity increases going up the column. That's because atoms of each element get larger going down the group. These atoms are electron grabbers. Valence electrons in the smaller elements are closer to the nucleus. That means, the positive attractive force that grabs the electrons is stronger than if the positive attractive force was farther away, like in a larger atom. This makes it easier for a stronger attractive, positive, force to grab and react with electron donors. Therefore, the most reactive elements are in the upper right and lower left corners. Reactivity decreases moving towards the center of the periodic table. Chemical notation is a form of shorthand, used to describe an element. The big X represents the chemical symbol found on the periodic table. The letter Z represents the atomic number, or the number of protons in the atom of the element. The letter A represents the atomic mass number, or the number of protons and neutrons. And the plus or minus at the top right represents the ionic charge, or valence. Neutral atoms won't have anything here. Go ahead and find the element uranium on your periodic table. The chemical symbol for uranium is simply U. The atomic number for uranium, or number of protons in one atom of uranium, is 92. The atomic mass number, or number of protons and neutrons, is 235. Since we know there are 92 protons, we can easily calculate the number of neutrons by subtracting 92 from 235 and getting 143 neutrons. Uranium-235, as it is called, is an isotope of uranium. Do you remember what an isotope is? Since we are dealing with a neutral uranium atom here, and not an ion, there is nothing where the ionic charge or valence should be. Note here that isotopes can be written in a slightly different format. The number after the dash indicates the atomic mass number, or the number of protons and neutrons in the isotope of the element. This is a sodium ion. Why is this an ion? Because there's a +1 indicated for the ionic charge, or valence. Since this is a positive ion, you should remember that this means sodium must have lost 1 electron. Sometimes, if the charge is plus or minus 1, the number can be left off and a plus or minus sign by itself is understood to mean +1 or -1. Can you figure out how many neutrons? Atomic weight is defined as the unrounded value of the atomic mass number, protons plus neutrons. Atomic weight is measured in atomic mass units or AMU. This is the atomic weight of chlorine. 35.4527 AMU. Or, you can just leave off the AMU and say 35.4527. Now keep in mind the exact number will vary depending on which periodic table you use, so you may not see the exact same numbers, but they should be fairly close. Elements whose atomic weights are shown in parentheses are radioactive. Now let's discuss the concept of molecular weight. Recall a molecule is two or more atoms chemically bonded. So molecular weight is simply the sum of the atomic weights of all the atoms in the molecule. Molecular weight is also measured in AMU. Here are the steps to calculate the molecular weight of a compound. First, identify all the elements in the compound. Here's a molecule of water. The chemical formula is H2O. It consists of two elements, hydrogen and oxygen. Next, determine how many atoms of each element are in the compound. The number in front of the atom indicates how many atoms are in the molecule. If there are no numbers in front of the chemical symbol, it means there is only one atom in the molecule. In the case of water, there are 2 atoms of hydrogen and 1 atom of oxygen. Now, look up the atomic weights of each element in the periodic table. It's important that you use the entire number given. Do not round. For hydrogen, the atomic weight is 1.0079. For oxygen, it's 15.9994. For each element, multiply the number of atoms of that element by the atomic weight of the element. The sum total of all the weights calculated is the molecular weight, expressed in AMU. The mole is a very important concept in chemistry. The mole is a counting unit. The mole has a value of, and you need to know this exact number, 6.022 times 10 to the 23rd power. This number is called Avogadro's number in honor of the scientist who discovered it. Now, as I said before, a mole is a counting unit. A mole of anything consists of 6.022 times 10 to the 23rd units of whatever that anything is. just like a dozen eggs equals 12 eggs. A mole of eggs equals 6.022 times 10 to the 23rd eggs. Now obviously, a mole is a very big number, while a dozen eggs would make a very large omelette. A mole of eggs would fill all the oceans of the world 30 million times. Gram atomic weight, abbreviated GAW, is defined as the mass or weight, in grams of a mole of atoms. Gram atomic weight is simply the atomic weight, expressed in grams. So, from the periodic table, we get the atomic weight of sulfur to be 32.065 AMU. All we have to do is express the same number in grams, and we get the gram atomic weight of sulfur, 32.065 grams. The significance of this is that 1 mole of sulfur atoms, that is, 6.022 times 10 to the 23rd particles, weighs 32.065 grams. Gram molecular weight, abbreviated GMW, is defined as the mass or weight, in grams, of a mole of molecules. First we calculate the molecular weight as we did earlier, and express that number in grams. Remember we calculated the molecular weight of water as 18.0152 AMU? To get the gram molecular weight of water, all we do is express that number in grams, 18.0152 grams. And in those 18.0152 grams, there are how many water molecules? That's right. 1 mole. 6.02 times 10 to the 23rd molecules of water.